Hi everyone. So last time we talked about uh, the relative basicities of the leaving groups, and we talked about that the acyl chloride is going to be the most reactive, then the ester, carboxylic acid and amide would be least reactive. Okay, so let's start from here today. A weak base makes formation of the tetrahedral intermediate faster. Now let's say this Y is a weak base. Okay, so if you look at the resonance contribution, Y with its lone pairs give its electrons to the carbon to form the pi bond. This pi bond opens up and then we can draw the resonance. Okay, so these are the resonance contributors of a carboxylic acid or carboxylic acid derivative. What happens when the base is weak? The weaker the base, if the base is weaker, the contribution is going to be smaller from the resonance contributor. With a positive charge on Y, okay, and the more electrophilic the carbonyl carbon. So the advantage of being a weaker base, the smaller the contribution from the resonance. So the resonance will be least contributed. So as a result, we will have more positive charge on Y. Okay, and then the more electrophilic is the carbonyl carbon. Carbonyl carbon would be more electrophilic. We want the carbonyl carbon to be more electrophilic because the incoming group then come and attack the carbonyl carbon. The incoming nucleophile is electron denser, but the carbonyl carbon, the more electron deficient, the more electrophilic carbonyl carbon would be the best. So having a weaker base, that can attribute having a least electrophilic character, most electrophilic character, okay, on the carbonyl carbon. Okay, a weaker base makes elimination from the tetrahedral intermediate faster. Since the resonance contribution also very low from the Y group, once the tetrahedral intermediate forms, so this is the weaker the base, it's faster making its strong conjugate acid. Okay, so the weaker the base, it makes it easier to eliminate and forms its stronger conjugate acid. For example, if this is chloride, hydrochloric acid would be the conjugate acid, forming it really faster. Okay. Carboxylic acid derivative can be converted only to a less reactive carboxylic acid derivative. Now here we have a acyl chloride. You're going to react it with methoxide. Methoxide, now between the chloride and the methoxide is a stronger base. So chloride is weak. Okay, so this can attack the carbonyl carbon, form the tetrahedral intermediate, reform the carbonyl group and leaves chloride, and then you have the ester. Now between the acyl chloride and ester, which one is more reactive? Acyl chloride is more reactive. So the more reactive we make to a less reactive one. So this now is not going to react with chloride. Okay, now you put these two together, the products, the ester and the chloride, there's no reaction because this is a stronger bond. This chloride, even if it forms the tetrahedral intermediate, chloride will still be the one that's going to eliminate and you're going to get back to this product. Okay, only from a weaker base you can make less reactive carboxylic acid derivative. So these are the reaction coordinate diagram showing you if you have a poor leaving group or a better leaving group or a same leaving group properties, how the progress of the product formation. Okay, less reactive meaning more stable carbonyl compound. Having a poorer leaving group, you can see progress of the reaction is going to be more more endothermic. Okay, has higher in energy. Whereas if you start with a more reactive, meaning less stable carbonyl compound, having a better leaving group, it will give you a more stable product, which is exothermic reaction, energetically more favorable, less energy compared to the starting material. If you have the same reactivity for the leaving group, then you will have about the same reactivity for your reactants and the products. Acyl chlorides. So the acyl chloride is, you have this acyl group, carbonyl group, alkyl group, and a halogen, acyl chloride. So this is specifically acetyl chloride because it has 2 carbons. Reactions of acyl chlorides. Now you know, out of all the carboxylic acid derivatives, the halogens, acyl halides, are the most reactive. So because of that, they can react with methanol, they can react with water, they can react with amines to form esters, carboxylic acids, and amides. Okay, so the acyl halide with a methanol, you can replace, you can leave this because this is very weak base, right? So this is a stronger one. It can substitute for the methoxy group and forming an ester. With water, carbon-chlorine bond, weaker base will remove and we can form carboxylic acid. With an amine again, you can replace the chloride group with amine to form an amide. Okay. Mechanism of the reaction with a negatively charged nucleophile. Now let's look at how an acyl chloride react with a alkoxide nucleophile with a negative charge. Pretty strong if it is a negatively charged. So it's going to go ahead and attack the carbonyl carbon. Carbon-oxygen pi bond breaks. Reform the pi bond. So between these two, the weaker bond breaks. And we know this is the weaker base. So that will eliminate and form the carboxylic acid. Okay. Mechanism of the reaction with a neutral nucleophile. If the nucleophile is neutral, for example alcohol, still with the lone pairs on the oxygen, act as a nucleophile, attacks the carbonyl carbon, forms a tetrahedral intermediate. Now since we started with the neutral molecule, when it attach, oxygen will still have the alkyl group and the hydrogen. So a base will come and grab that hydrogen and make it a neutral. Okay, so now we have this negatively charged oxygen between the chlorine and alkoxy group. This is the weaker link. So the weaker base would be eliminated and you can get the ester. Okay, so this is the mechanism if you have a neutral nucleophile, and this is the mechanism if you have a nucleophile with a negative charge. 2 equivalents of amine or ammonia are required if you are going to make an amide from an acyl chloride. So 1 equivalent of the ammonia will first add to the carbonyl carbon. We'll see the mechanism over here. No mechanism. Okay, don't worry about it. Then what's going to happen is 1 equivalent of the ammonia will add to the carbonyl carbon. Pi bond opens up, forms the tetrahedral intermediate, reform the pi bond, and then the chloride left. We can leave the chloride. So that will give you this amide intermediate. Okay. Now with HCl and amine, another equivalent of ammonia will protonate this hydrochloric acid. Ammonia is not going to protonate hydrochloric acid, but the hydrochloric acid will protonate the ammonia and form ammonium chloride salt. Okay, so that is to protect. And sometimes what happens is if you don't do that, so this nitrogen can grab a proton. Okay, 1 equivalent of amine or ammonia is a nucleophile, the other picks up the proton produced in the reaction. So the proton produced in the reaction, hydrogen, H plus ion, will be picked up by this one. So we normally use 2 equivalents to make the amide from acyl halide. So this is the ester functional group, methyl acetate. So this is the methyl part, and then the 2 carbons, acetate, carbonyl group, and this is the oxygen in the ester. Reaction of an ester with water. Ester is not very reactive. It's less reactive than acyl halide, and water is a poor nucleophile, so it needs a catalyst. Normally, esters can undergo hydrolysis in the presence of water and an acid catalyst. Hydrolysis is adding a water molecule across this carbon and oxygen. So the OH of the water molecule will end up being on this side. Hydrogen goes to this side. So our end result is going to be carboxylic acid and methanol. Hydrolysis is a reaction with water that converts one compound into 2 compounds. Ester will give you carboxylic acid and methanol. And similarly, esters can react with alcohol. So in the hydrolysis with water, OH went to this side, hydrogen went to this side. Similarly, you have this part in ethanol. Okay, the way it's going to break is H plus goes to one side, and then oxygen with this alkyl group goes to the other side. So the hydrogen goes to the methoxy part, and then the other part goes to here. It forms an ester and alcohol. So we call it as alcoholysis. It's a reaction with an alcohol that converts one compound into 2 compounds, ester and alcohol. This alcoholysis reaction called a trans-esterification reaction. One ester converted to another ester. And the esters can also react with amines. Okay, remember the resulting amide is less reactive compared to the ester. So esters can react with amines, methylamine. You heat it up, so then this group will be lost. So you're going to be getting the amine. Nitrogen will attack the carbonyl carbon and then reforms the carbon-oxygen pi bond. So between carbon-nitrogen and carbon-oxygen, this is the weak base, it eliminates, and we can generate the amide group. So we call this as an aminolysis, reaction with an amine that converts one compound into 2 compounds. So the ester with amine give you amide and an alcohol. So this is the ester. Excuse me. So we have already seen when you have a carbonyl group, you do a reaction in acidic medium. What's going to happen? Carbonyl oxygen get protonated. So there are 2 oxygens. So here oxygen and this oxygen, and on between these 2, carbonyl oxygen has a greater electron density compared to this oxygen. So that's why the acid protonates the atom with the greatest electron density. Oxygen will protonate, giving protonated carbonyl oxygen. We can also see that with the resonance structure right here. If you draw the resonance for the ester, this lone pair forms the pi bond and carbon-oxygen pi bond breaks. Oxygen will get the negative charge, this oxygen. But this oxygen would be electron deficient. This is electron rich. So this atom has the greatest electron density, and this oxygen has less electron density, and it's already having a positive charge. Okay, so as a result, when you add acid to ester, always the carbonyl oxygen that gets protonated. Okay, with that in mind, let's see the mechanism for the acid catalyzed hydrolysis of an ester. Now, what is hydrolysis? Hydrolysis is an addition of a water molecule across the carbonyl carbon and oxygen of the ester, between this carbon and oxygen. Okay, first thing, in the presence of an acid, carbonyl oxygen get protonated from the acid. So it will be now a positively charged, having oxygen 3 bonds. Now the water molecule, which is going to be your nucleophile, adds to the carbonyl carbon. and form the tetrahedral intermediate oxygen. This oxygen still have its two hydrogens on it, so it's positively charged. The base come and will grab the hydrogen to make it a neutral intermediate. Okay. Now after the tetrahedral intermediate 1, removal of the hydrogen become intermediate 2. Equilibration of the three tetrahedral intermediates. Either OH or CH3 can be protonated. All of these have similar properties, these three oxygens. Any one of these can be protonated. Okay, but if this or this get protonated, we're going to get back to our reactants. Do we want that? No. So we want to go forward. So we're going to go ahead and protonate this guy over here. So when you protonate this, now you have a protonated alcohol. Okay, OH, CH3, a positively charged. Now this one is ready to lose. If you try to lose a hydroxide, which is not a good leaving group, but here you have a protonated alcohol, neutral molecule, a weaker link, weaker bond, so oxygen, carbon, pi bond forms, and then the carbon-oxygen bond breaks and leaves a methanol as a leaving group. So then the base comes and grab the additional hydrogen, and we can get back to our acid. That is the acid catalyzed hydrolysis of an ester. Now, what do we do if you want to drive the reaction forward? Use excess water to drive the reaction to the right. If you are doing a hydrolysis, just like this. So we put a lot of water. Okay. So this is your ester. You add a lot of water, so we can drive the reaction forward. The more reactants we have, according to the Le Chatelier's principle, the reaction will favor the direction where it can get rid of the excess reagent and make more products. Okay. And another reason why in the presence of acid, oxygen get protonated, it helps the carbonyl carbon more susceptible to nucleophilic addition. Protonation of the carbonyl oxygen increases the susceptibility of the carbonyl carbon to nucleophilic addition. This one with oxygen on with hydrogen on the oxygen, more susceptible to addition of a nucleophile. This one is less susceptible to addition of a nucleophile. Okay. Always, if a reaction or an intermediate or a compound has a positive charge, it would love to get rid of that positive charge. So as a result, a nucleophile will be more readily attacking this carbon. So this carbon-oxygen pi bond breaks easily and give a neutral oxygen atom here. Okay. Also, another thing is the protonation makes the leaving group a better leaving group because it's going to leave as a neutral molecule. So this is the leaving group in acid catalyzed ester hydrolysis. Remember, we have seen this one. This protonates, so it can leave as a methanol. But if you have this molecule, the leaving group in uncatalyzed ester hydrolysis, it's going to leave as a methoxide, an ion, strong base, kind of. Okay. Transesterification. So transesterification is a reaction of an ester with an alcohol. So you start with one ester and you're going to get at the end with a different ester. So this is ester you start with, the methyl ester. You add propanol, 1, 2, 3 propanol in the presence of hydrochloric acid. Now this ester group is, this alkoxy group is left, and you would end up getting this alkoxy group. An ester is not very reactive and alcohol is a poor nucleophile, so a catalyst is used. And this is the reaction. No. This is the mechanism for hydroxide ion promoted hydrolysis of an ester. Okay. We don't have the mechanism, but it's okay, you don't need it. The mechanism for hydroxide ion promoted hydrolysis of an ester. It's a base promoted. So the hydroxide attack the carbonyl carbon, carbon oxygen, pi bond breaks, forms tetrahedral intermediate. So this is a base. So in the presence of a base, we never protonate this oxygen. There are no acid to protonate. Okay, and then the alkoxide ion, this is stable in basic medium. So it reforms the carbonyl bond and then leave methoxide. Okay, so once the methoxide is lost, now we have acidic hydrogen in the carboxylic acid. So the methoxide takes this proton and gives us carboxylate anion and methanol. So since this has been done in the basic medium, you can see since the carboxylate anion is being formed, this is irreversible reaction. How hydroxide ion increase the rate of the reaction? Hydroxide ion is a better nucleophile than water in ester hydrolysis. Collapse of the tetrahedral intermediate is faster in a basic solution. So this, you can see the transition state for elimination of methoxide from a negatively charged tetrahedral intermediate. Okay, negatively charged O minus forms the carbonyl bond and then it leaves, more stable transition state. This one shows transition state for elimination of methoxide from a neutral tetrahedral intermediate. If OH is neutral, oxygen is going to be electropositive. It has a delta positive on oxygen. So this is less stable transition state, having a positive charge on oxygen. Okay. So the base, having a base, will help to increase the rate of the reaction. Acid catalyzed ester hydrolysis is reversible. Hydroxide ion promoted ester hydrolysis is irreversible. Okay, let's see. Now this is again ester hydrolysis with water in the presence of acid. So we are getting carboxylic acid and methanol. In the presence of a base, we form carboxylate anion and methanol. We have seen this mechanism. See, carboxylate anion. So the negatively charged carboxylate anion do not react with nucleophiles. So as a result, this is not reversible, whereas this is reversible. Reaction with an alcohol can be catalyzed by an alkoxide ion. Now ester, so this is trans esterification. If you have this ester, you add excess ethanol, in this case, whatever the ester you want to make. And then if you have an ethoxide ion, alkoxide and the same ion that you want to replace the ester with, you use the same alkoxide ion that would help to form your product more and also faster. Only hydrolysis reactions can be promoted by hydroxide ion. Okay, we'll stop here and then we'll start the next session in the